OK になったら言ってください。始まったら言ってください。始めます。はい。ですね、じゃあ、イーブニングセクションを、始めたいと思います。今日は、第1回目の、イーブニングセクションで、アドリアン、ビトさん、先生の、プレゼンテーションです。ニューラルサウンドシンセス、ということで、ウェブサイトにも、概要がありますが、オーディオ関係のですね、ニューラルサウンドシンセス、についてお話しさせていただきます。で、アドリアン・ビトンさんは、イルカムの、研究員として、今も、深層学習モデルの、音の合成について、研究を、しております。では、始めたいと思います。OK, c'est bon, tu peux commencer.
Super. So, hello everyone. I am Adrien Bitton. Thank you for introducing me, Professor Goto. Today I am talking about sound synthesis with neural networks, which is part of my PhD at IRCAM Paris.
私の名前は、アドリアン・ビトンです。まず、紹介をありがとうございました。イルカムでは、博士を、取ったばっかりで、今日話すことは、その研究の際に行われた、ニューラル、ネットワーク、ニューラルサウンド、シンセスについてお話ししたいと思います。
So my PhD is supervised by Professor Esling, that you maybe know, and Professor Agon at IRCAM. And I was a Japanese Society for Promotion of Science Fellow for 7 months from last year October. And so I came to University of Tokyo Machine Intelligence Laboratory. And we also organized a seminar on music and AI with Gaidai earlier this year.
まず、イルカムの博士号では、エイスリング、先生と、アゴン先生、イルカムのですね、の、下で、博士号を取りました。で、日本にはですね、2019年の10月から2020年の4月まで、東大の、マシンインテリジェンスで、JSPS の、奨学金の、を取って、日本を滞在しました。滞在中は、東京芸術大学で、AI と、サウンドシンセスについての、学会も、企画、しました。
So my topic of PhD, so I'm using generative neural networks to synthesize audio, and the aim is to learn meaningful controls for musical purpose. So for example, we will talk about sampling, interpolation, or resynthesis with control over some style parameters, and learning representations for audio that allows musical interactions.
まず、私の、研究課題課題分野なんですが、ジェネラティブ、ニューラルネットワークの、それは、オーディオシンセスのための、ものだと。で、それから、音楽の、サウンドシンセスを、操作する、コントロールする、もっとインタラクションっていうので、その意味を持った、コントロールっていうどういうことかというと、具体的に、サンプリングとか、リシンシスとか、または、インターポレーションですね。あとは、スタイルの、音楽スタイルの、そのあるスタイルのモデルの、徐々な変化ということになります。それから、アンスーパーバイズベーセーションラーニングだから、学習なしの、その、オーディオとか、音響ですね、音響学について、研究を行っています。Okay.
So in the presentation, I focus on audio, which is, for example, different than symbolic music processing. You might think of automated composition, like generating scores, but we focus on audio, and we focus on parameters of music that we can associate with audio.
今日話すことは、よくある、オーディオ、音楽のデータでね、作曲するための、パラメータとか、そういうものではなくて、オーディオシンセスについて、お話しします。ですので、シンボリックな、作曲の、プロセス、または自動作曲についての話ではないです。それから、音楽の、サウンドシンセスのパラメータですねっていう、ものについて、話します。それは、スピーチシンセスとは、異なるものです。
And my research on synthesis uses neural networks, which complement or like can replace hand-engineered hardware and software. So there is these two fields that are not yet breached. So this is not yet max MSP, but there can be some prototype and use case where we can complement neural network synthesis and hardware and classical hardware and software, which I am interested in.
ニューラルネットワークの、サウンドシンセスについて、話しますが、それは、ある、人間で、行われる、ものではないと。で、MaxMSP の、今現在使っているのはインターフェースの段階で、完全な、その Max に、移行したわけではないですが、今のところ、プロトタイプ、が、近いうちにできるだろうということです。Okay.
So in the presentation, in the first place, I want to introduce the problem of neural synthesis and the challenges that we face in the field, and introduce some reference models. And later, I will present some personal experiments in music sound synthesis, and I will finish with some ideas and discussion.
ニューロサウンドシンセスの、についてなんですが、まず、個人的な、実験というか、というので、ニューラル、グラニュラサウンドシンセスとかですね、音色について、話をします。
So when we think of classical sound synthesis, we think of an interface with some control parameters or some possibility to use MIDI to compose, and this will control a complex chain of devices that will create an output audio. So we have a lot of parameters that are associated with electronics, hardware, or digital signal processing. And based on that, we want to produce audio that is diverse, high quality, and predictable and novel.
通常の、伝統的な、サウンドシンセスというのは、いろんな、パラメータを、操作するとか MIDI の、パラメータを操作するっていうので、それが、ハードウェアとか、ソフトとかっていうものを、介してで、オーディオ、の、出力になると。っていうので、いろんなその段階では、いろんなさまざまなものとか、質とかある程度、予期できるものとか、新しさなどの、条件が必要となってきます。Okay.
So the limitation of classical sound synthesis, so from the user viewpoint, I will start, is that to assemble and control this pipeline of devices, it takes a lot of time. It requires a lot of expertise until we achieve a certain control combination that will produce the sound that we want. And from the engineer viewpoint, well, we want to create new tools for creativity, and there is increasing complexity to design these new tools as we want to improve, enhance creativity and allow new synthesis techniques.
これまでの、サウンドシンセスっていうのは、それを、できるようになるまで、随分、時間がかかるというか、非常に、その専門家に、専門的な、知識が、要求されたと。で、それから、新しい、技術者の立場としては、新しい、道具っていうのを、作りたいわけですが、それによって、複雑性っていうのが、増すっていうので、創作に関しては、むしろ困難になるっていうような、ことです。
Okay. And so the promises of neural sound synthesis. So what do we hope with neural sound synthesis? So like from the engineer viewpoint, all these techniques that we don't know how to design or that we have not developed, can we find these solutions with machine learning when handcraft work, human work is not satisfying, is limiting, and are the new tools of machine learning able to actually enhance or complement human creativity, not replace, but be useful tools for human creativity?
ニューラルサウンドシンセスによって、我々が、簡単に、できなかった、ことが、解決、できるのではないかと。それから、このような、新しい、道具によって、創作に関しての、創作が向上するというか複雑性が増すというか、さらに、高いレベルになるということですね。っていうことができないかというのを、考えています。
So in neural sound synthesis, the idea is that we replace all the handcraft tools, all the synthesis pipeline with a neural network that will learn its internal parameters based on statistical learning, observation of the data. And in the end, we would like to have meaningful control over the neural network. So for example, control above semantic properties or customized control for users, and that these controls allow us to produce an output audio that is diverse again, that is high quality, predictable, and novel, but with the use of neural network synthesis.
これまでの複雑な、手作業に、変わってですね、統計的な、学習によって、ニューラルサウンドシンセスができるのではないかと。っていうので、意味のあるコントロールのパラメータということは、セマンティックな、部分であるとか、ある、条件というか、前も予期されたというか用意された、コントロールですね。っていうものに、から、実際に、音響合成が、できないかというのを、考えています。
In the first place, so this learning problem can be thought as a supervised problem, which means that we have a data set of audio samples, of waveforms, with some labels that we are interested in. So for example, we can say note classes, like what is the pitch, what is the octave, what is instrument, the playing mode, different things. And so we have data paired with labels, and we would like to learn a generator that allows us to generate data from the labels that we are interested in.
教師ありの、学習で、そのある、音響を、なんていうのかな、レーベルをつけると、あるカテゴリーを、つけるっていうので、それは、ピッチとか、音色とかっていうものに、値するんですが、そのような、ことをもとにして、音響合成っていうのが、できないかっていうのが、一つです。
So in that case, so supervised generative modeling is still very limiting for several reasons. The first reason is that annotated database are not freely available. It requires human annotation, which is time consuming and expensive. But the main problem is that we actually cannot label and quantify all the sound variations that we can be interested in. So for example, we cannot quantify easily the difference in between sounds.
学習、教師ありの、ものに関して、問題っていうのは、それが、随分、重労働であるっていうことと、あと、そのような、音色というか、っていうものが、具体的に、その分類分けできないと。で、その、出力の部分っていうのが、新しくて表現あるものとは必ずしもつながらないかもしれないということです。
So for that reason, the output that we will get from the neural network cannot be really novel and expressive. So for example, again, if I have this generator as before, I will just sample notes based on a certain label, and then I just change label and I get another note, which is basically what is doing a classical sampler, like for example in Ableton or music production. And for that reason, so I am more interested in unsupervised learning, which means that we cannot label the information that we are interested in. So we want to learn the representation of the data, so the Z representation, and we would like to use the representation that we learn of the data to generate new data.
その通常の、サンプラーでは、例えばエイプルとライブとかの、でただ単に、ピッチが、変えるだけだと。で、その、基本的には、学習なしで、ごめんなさい、教師なしで、学習をさせて、で、それを、意味のある表現に、変換したいっていうので、そのデータから、独自で学んで、その表現したいっていうのを、目的としています。
And so the question that is raised is because we do not control the generator with labels that we have annotated, with labels that we know, but we control the generator with a representation that is learned by the model from the data. Question is, can we still control something meaningful and intuitive with this representation? So, for example, one thing that is important is that this representation is of low dimensionality, that is less parameters, so that when we control parameters, they have a bigger effect and they are more intuitive for the user.
意味があって、もっとなんていうのかな、直感的な、パラメータっていうのを、学ぶことができるかっていうのがあって、ちょっと難しい表現だったんですけど、ある、流れ のような、もので、そのある部分からある部分を、ちょっと意訳ですけど、予期するっていうことで、もっと豊かな表現が、できないかっていうのを、考えています。
So different type of like classical frameworks for learning this representation and the generator. So I will present two models, autoencoder and generative adversarial networks.
Sorry.
And,
can you say it again?
So I will talk about two types of models to learn this representation from the data along with a generator that allows to create new audio.
I don't quite understand this phrase.
Oh, sorry. So let me introduce two types of models to learn this representation and the generator.
Okay,
So the first
I want to
type.
translate what you said. まず、2つのタイプの、音を、作り出すことについてお話したいと思います。Okay, just first one.
Okay, so the autoencoder, so basically the decoder, which is the generator, is paired with an encoder, and so the encoder will take the data, will compress it, and will give the representation to the decoder, which learns to reconstruct the data.
まず、自動のエンコーダーで、一度、エンコードして次に、デコードするわけですけど、その、この部分ちょっと私も、すごく分かりにくかったんですけど、その、デコードするときに、その、再び、作り直すとかいうような、ことだと思います。Okay.
And the second type of model class is generative adversarial network, GANs. So basically, the generator here is paired with a discriminator, D, and we feed the generator with samples from a continuous distribution, and we train the generator to produce audio samples that are realistic. For that, discriminator is trained at distinguishing true X and synthetic GZ, while the generator is trained at being seen as true by the discriminator, so at being realistic.
You mean the generative adversarial network is their
Yes.
sort of discriminator, which does what?
Yes.
What does it do?
The discriminator. So the discriminator sees true data X and sees synthetic data from the generator GZ, and it is trained at classifying is it true data or synthetic data, and the generator is trained at being classified as true, so that it produces data that is similar to the true data that we are training the model with.
この方が非常に難しいんですけど、その、ジェネラティブ、アドバーサリアルネットワークについてで、ある意味での、分類ではないなんだっけフィルターのような、ディスクリミネーターだから、差別化というかっていうので、理解が正しければ、すいません、これ非常に難しいので、その、正解と判断するときにそれが、それが学習されていると。で、それが、サウンドシンセスされるということです。In the case of the false, what is the what is the case of the false?
The case of the false is that the data generated, so the synthetic data from the generator is is classified false by the discriminator because the discriminator discriminates between true data from the database and generated data from the generator.
その正しいか、間違っているかっていうので、その判断っていうのはその学習データから基づいているという、ことだそうです。OK。
So as we have we just need a data set, just waveform samples, and we can learn a representation and a generator. So there are other types of models that we don't need to talk about, but we can also mix, for example, labels and unsupervised representation. So for example, having a conditional generator, semi-supervised.
そのオーディオのデータがその複数のデータですね。それによってある程度のモデルになるわけですが、この学習半分の半教師の学習というようなことだと思います。ごめんなさい。ここ非常に難しくてあまりうまく訳せません。はい。OK。
The challenges that we face with neural sound synthesis, so from the input of the model is to learn, control any interaction that are useful for music composition. So for example, this parameter can be short term, for example, the loudness and pitch envelope of a signal, or they can be a higher level or longer term. And these parameters doesn't have an explicit time structure. So the model must learn the temporal structure of the audio.
作曲のための、音楽のパラメーターで、意味のある、表現の仕方っていうので、短い、段階では、音の強さとかピッチっていうので、その、時間軸の、進行によってそれぞれの、フレームで表せるわけですが、少しというか、高い、レベルでの、話ではそれと、ある単位になるわけですが、それが、その、時間軸のある、長い単位で、あまり明確な形で、そのピッチとか、音の強さとかっていうものではなくて、ある程度その、分類分けできるような、その、一つの、カテゴリーというような、ものと、その二通りに、表すことができます。それが、インタラクティブに、コントロール、インタラクティブと、コントロールの部分を学習できるというような、インプットの部分です。
And for the output of the model, so we want the sound synthesis to be efficient, which means a high quality signal and a meaningful signal. And the challenge is that audio quality is based on local property and phase, so spanning around 1000 waveform samples, and the macroscopic properties are spanning a much longer term structure, 10, 100,000 samples, and the model must control all these temporal scales at the same time.
まず、高い、質の、部分なんですが、それは、1000、ウェーブフォーム、波形のサンプルに、基づいていると。しかし、もっと、もう少し、長い、時間タイプ部分に関しては、1万から、10万の、サンプルっていうので、それは、ある、単位で、意味が、持てるような、部分です。で、それらというのが、そのアウトプットの、オーディオシンセシスの、部分に、該当するということです。
And ultimately, that's one challenge that is overlooked into nowadays research, but is also for the user. Is a neural network real-time capable, or can we use it into an embed hardware platform, or like a portable instrument, laptop, and how much does it cost for training and database?
ラップトップなんかで、学習させるのに、どれぐらい、時間がかかるかっていうのが、少し疑問点としてあります。
So now I will talk about a slide to audio in the literature, and the main ideas that I want to highlight is what is the sound representation that we consider, and that is related then to what neural network architecture we will train, and what interactions we achieve with the model.
上から2行目の、この、部分に値するんですが、音の、表し方ですね。でそれが、ニューラルネットワークの、構造というか、どのように関係するかと。でそれらが、最終的に、どのようなインタラクションできるかっていうのが、一つ、課題とあります。
So the first reference model for waveform synthesis was WaveNet, and its application for music into NSynth, and it is based on waveform causality, so that each individual waveform sample come one at a time, like in a causal order of time, and so we can learn the waveform by predicting every new sample based on the previous samples of the audio.
ウェーブネットっていうのが、ウェーブネットの、N シンスっていうのが、一つ応用例なんですが、それというのが、それぞれの、サンプルの、波形に、影響し合うっていうような、方法で、構造として、考えられる方法です。
So this way to model audio has limitations because the sequential sampling, one individual sample at a time, is very slow, and the representation that the model learns is very local. So, for example, for just like maybe like 1 second of audio, you need to see 44,000 waveform samples. So you need to have a very, very large architecture, and yet you only see a very local representation of time.
What do you mean the local representation in this case?
So what I mean by local representation is that we consider a neighborhood of waveform samples. So by the neighborhood, if we want to have a large neighborhood, a large temporal context, you need to see a lot of information of waveform samples. So the model is limited at seeing only a limited temporal context because it's operating on individual waveform samples.
1000ぐらいの、波形が、連続的に、サンプルとしてあるわけですけど、その、ローカル、リプレゼンテーションっていうのはその、すぐ、その近い前後の部分を、見て、判断するわけであって、長い単位であれば、非常に、大きなデータになってしまうと。っていうので、非常に、限られた、範囲で、前後で判断するという、ものです。Okay.
So this WaveNet model is not very efficient for music sound synthesis, and now another model, the symbol to instrument neural generator, was proposed specifically for sound synthesis of musical notes based on an audio representation along frames. So each step is a full audio frame, a full signal window.
先ほど話したのは、実際にはあまり、効率の良くないものだと。っていうので、少し考えられるのは、少し長いタイプの、オーディオの、表現の仕方っていうので、このなんか大きな単位で、判断していくというようなものですね。言い換えると。はい。OK。
So it allows sampling musical notes. So by giving at each time step a velocity, an instrument, a pitch, and a time position, and then this sequence of frame is upsampled to a waveform by the generator. So in that way, it's more easy to model long temporal structure because each step is a whole frame of audio, and also because the reconstruction is like the prediction is optimized on magnitude spectrogram and not individual waveform samples.
ちょっとここも非常に難しいんですけど訳すのは、そのwhat do you mean upsample?
Each step, like in the figure, there is 265 steps. So each step of the model is corresponding to a whole window of audio. So maybe one step is 2048 waveform samples. So one step is upsampled to these 2000 waveform samples. So that's why we can more.
So it's
so that's why we can more. Sorry.
200 sample is get together to represent as a sort of the
yes.
200ぐらいの
like
一つの塊として、サンプルを扱うと。っていうので、その効率が、むしろその、方法で良くなるっていうことです。Sorry, I didn't quite understand this part. Sorry, I had to ask you a question, but
yes.
Yeah.
So basically, the model is making predictions frame by frame, not waveform sample by waveform sample.
そのそれぞれのこのサンプルをやってるんじゃなくて、ある単位で予期させるというかっていうのがむしろそのような方法で効率が良くなるということです。Okay. So I'm getting.
So for example, in this case,
part, yeah.
the model. How? Yes, sorry, it's also technical.
Yeah.
But so basically, the figures that I show with 265 steps, it's for a 4-second audio. So
250.
when this model is making 206, so when the model is making 265 prediction, for example, WaveNet would have needed maybe 100,000. Because WaveNet is on each waveform sample, and this one, every step is a whole frame of thousands of samples.
So yours is
So that's why it's
255.
more efficient.
255の、一つの塊としてで、先ほどのウェブネットっていうのを、1000っていうのでだから、その、今の、255っていうのは、もっと効率がいいという、ことです。
So this model was good at modeling time on frame level, but not very expressive because it is based on a fixed category of not labels. And so now I will instead present another model that is based on low-level features without temporal modeling. So that is this differentiable digital signal processing DDSP model.
これは、少し違う方法で、DDSP っていう、方法へこれからお話ししたいと思います。
So it's based on a decomposition of sound between sinusoid, like partials, and a stochastic component. And the generator is modular. It is based on an additive harmonic synthesizer combined with a noise subtractive synthesizer for the stochastic part.
サイン波に、分解されているわけですが、それと、統計的な、方法で、合成されると。でその際に、アディティブシンセスと、その、サブトラックシンセスの、ノイズからサブトラックシンセスの方法の、組み合わされた、方法が、用いられます。
And it uses here a low-level conditioning. So it is a pitch and loudness envelope that are used to control the harmonic and filtered noise component, plus a learned dead feature. So this is expressive, as we can continuously modify the parameter, but it is not learning the temporal structure.
低いレベルでの、方法で、ピッチ音の高さとか、音量というのが、エンベロップで、表されるとっていうようなものです。
And so lastly, I wanted to show one type of GAN, generative adversarial network model, that was recently proposed for learning MEL spectrogram to waveform synthesis. So to learn like real-time vocoder.
この、メル、ガン、っていうものは、ある意味での、リアルタイムの、フェーズボコーダーっていうような、ものです。
So in that case, I call the conditioning unequivocal, because for one spectrogram, there is one specific target sound, and it is just needed to reconstruct the phase to generate the audio. So for that, they use fully convolutional GAN, generative adversarial network, and a discriminator that is working on several resolutions, so that it will learn different frequency bands of the audio. And this model can be used as a vocoder, so inversion to MEL spectrogram, but also it can be pipelined with other models. So for example, text to speech spectrogram to audio, or it can be also used to generate audio from another representation.
This spectrum is how is it related with the diagram that you show now?
With the discriminator?
Yeah.
So the MEL spectrogram is input of the MEL GAN generator, and the MEL GAN generator is producing the waveform, and the waveform is given to the discriminator. So then this discriminator is receiving true audio and like wrong audio. For example, audio with a phase with the wrong phase, and it will learn to discriminate between the two, so that the MEL GAN generator produces audio from the MEL spectrogram that has the correct phase.
So MEL spectrum is sort of the input of a MEL Melgan.
Yes, it is the input.
And then the
Yes, it is the
within
input.
Melgan, it's discriminate. So and then it generates sound at the end.
It's generating sound, the generator,
Yeah.
and the discriminator is taking the generated sound and the true sound, and it's learning to discriminate what is the wrong sound and the good
Okay,
sound.
okay.
So, for example, if you okay.
一番下のですね、メルスペクトラムっていうのが、そのスペクトラムなんですけど、それが、メルガン、というものに、入るわけです。で、その中で、差別化っていうのの、学習をして、で最終的に、音が、合成されるというものです。はい。OK。
So, for example, if you know about Griffin-Lim algorithm, which is a standard algorithm for generating audio from a magnitude spectrogram, you hear that it has a lot of artifacts. It doesn't sound very good. So the discriminator, for example, will learn to distinguish between the clean audio and the audio with a phase artifact. And then because it is used with the Melgan generator is trained at producing audio without the phase artifact.
この位相がこのその差別化の部分で関係してくるとということを言ってるだと思います。はい。Okay.
So now I will talk about some of my experiments. So the first one I will present is about neural granular sound synthesis. So the idea of this experiment is to have two representation levels. One that is for short-term features and one for long-term features. So the short-term features allow to do the variable length interpolations and textures, and the long-term level allow to generate samples with a fixed length temporal structure.
まず、この、2つの、タイプがあって、で、1つは、短い、時間軸ということで、それが、その、インターポレーションで、そのある、その大きな単位に、なっていくというものです。
So, for example, if I play with the tempo, like with the short-term level,
まず、
I can
短い、
make this type of interpolations. Can I play audio?
Okay.
So that is a smooth, acoustically smooth, or I can then use the upper level to sample audio that has a consistent temporal structure. So, for example, a violin note. So we can hear like that is along giving this tremolo, or playing like a drum hit that is with the normal envelope, with like a hitting envelope.
Okay.
And the second experiment that I will talk about
2番目の、
is
実験。Okay.
And the second experiment that I will talk about is to learn a discrete representation of timbre, so a representation that is invariant to audio levels, to loudness, and use this representation for doing instrument conversion, like transferring the timbre of one instrument to another, or to do audio synthesis controlled with acoustic descriptors.
ある音からある音に、徐々に、変化するという、ものですね、これは。Okay.
So, for example, if we hear, like for the instrument conversion, if I take input audio clarinet,
クラリネット。
and then, for example, I want to play it, I want my model to convert it into a violin.
バイオリン変化してくる。
Or let's say I have a model that is trained on singing voice, and I want to generate singing voice that is organized along the fundamental frequency. So increasing fundamental frequency.
まず、歌ってる、声が、モデルとして学習させて、で高音によって、それが、変化していくという感じ。
Or, for example, I could also control it with a centroid, which is not pitch, but based on the distribution of the spectrum. So that is the same model that is controlled with different audio descriptors.
Okay.
So, so for neurogranular sound synthesis, I propose to use a two-level autoencoder. So the first autoencoder is learning a representation of waveform windows, as in the symbol to instrument neural generator. And these features are given to a second autoencoder that will learn to embed series of waveform windows organized along time.
ローレベルの、そのものから、up level is the framework temporal model. What does it mean?
It is a recurrent model that is learning to generate waveform windows organized, ordered in time. And the low level is just learning a representation of individual windows without temporal relationship.
So low level is only something to be learned, and upper level is as a result.
They are learned together, but the bottom level is just learning to generate audio from a representation that is not organized in time, and the upper level is learning to organize the first representation in time. So then, if I use the upper level, I can generate a signal that is consistent in time. For example, a note that is doing a tremolo, or a drum hit that is first doing an attack, a decay, and a release.
ちょっとこの辺りからもう本格的に分かんなくなってきたんですけど、私も、まず、ローレベルっていうのが、その短い、なんていうのかな、サンプルのレベルで、アップレベルじゃ、その長い単位なんですが、それ、2つとも、両方とも、学習、し合ってるそうです。ちょっとこれは、正しく訳してる。いいんですけど。
And in that case, so the low-level VA, I train it to generate audio as a subtractive synthesizer. So for each window frame, there is a filter that is produced by the generator that is filtering noise in order to produce the desired audio.
なんだっけ、サブトラックシンセスか。それが、the noise is added on the middle.
the noise is not learned. The noise is just a noise source, like for example
ノイ
white
ズは、
noise,
そうい
and
う、
then
ソースがあるそうです。
and the output audio is the result of the noise source being filtered by the model. So for each window of noise, there is a filter that is creating the desired output window of audio.
そのノイズから、欲する、音へと、サブトラックシンセスの方法で、フィルターされて、で最終的に出てきた音っていうのが、その結果だそうです。
So the interaction that I propose with this model is with these two levels of generator is so using the lower level that is smooth for the low level acoustic but without temporal structure is to do interpolation, or for example to modulate interpolation, doing for example forward backward to give some kind of rhythm even though it doesn't learn temporal structures.
ローレベルは、音響の変化では、スムーズなもので、その、徐々な変化っていうのが、前後に、進行することができるんですが、それっていうのは、必ずしも時間軸に、基づくものでは、なくて、インターポレーションする、ものだそうです。Okay.
So for example, we can hear a linear pass. As before. Or a linear pass, like now it will be drum sound, I
さっき
think.
のが、
A linear pass that is going forward and backward.
これが、前後にする。
So here we hear more like an idea of rhythm, forward, backward. So that's some interaction with the first level decoder that I experiment with. And the higher level model that is learning audio with a temporal structure, so we can do sampling. So for example, a snare hit, so that's produced from the model, or we can use it to do interpolation of temporal structure, which means I have different sounds that will evolve. I will sample sounds that evolve in their temporal structure. So for example, here we will hear a first like snap sound, and the second sound is more sustained, and the third sound.
Okay.
So this will be like interpolation of temporal structure. So here the model learns to produce different sounds, and we can control how they evolve a long time.
Okay.
And so I apply this to make a machine. So I use MaxMSP as a control interface through Open Sound Control, and have a server with a pre-trained model that is producing audio and filling the buffers for the step sequencer in MaxMSP.
これらを、OSC でMaxMSP を、インターフェースとして使って、で、OSC から、Python へと、データを、送るそうです。And the link below is sorry. Before you go, that link below, everyone can download this. Or not yet?
It is demonstration materials. It is just like there are some videos and some audio.
その下のリンクは、
But
デモンストレーション用の、ビデオとか、それ、it's not the source code.
If someone wants to, like someone should send me an email to ask because the code is complicated. So
Yeah, sure.
I cannot just put it online. It's too complicated. So
そ
so I
そこに
yeah
ソース
I
コー
don't
ドがあ
have
るわ
like
けではないそうです。OK。
But if someone is sending me email, I am happy to send codes or like to adapt codes or like to discuss implementation. But just it's not plug and play. It's not plug and play. It's too
もし、
complicated.
興味があれば個人的に、連絡もらえれば、コードを、渡すことができますが、その、使えるようになるにはそんなに、簡単に、できるものではないそうです。Okay.
So the second model that I want to talk about is to learn a discrete representation. So this time the encoder
Excuse me,
is
before you go on,
learning
how much do you have left?
Yes. Oh, okay. It's yeah, we are running out of time.
No,
Yes. So I will go.
yeah,
I can go faster.
okay.
So as we are running out of time, but basically in that case, the model has only a set of features that it can use to produce audio. It's learning these features from the data, and these features are invariant from loudness, so that they are related to the timbre of an instrument.
この例は、その、特徴を、強調するっていうような、方法の、サウンドシンセスの方法です。Okay.
And so how to interact with this model? So the first thing is more implicit control. It is because it learns features of an instrument. If I give it another instrument, it will resynthesize this instrument with the features of the instrument it has learned from.
Okay.
So that's how I do, for example, this transfer. If I give a clarinet and I train a model on trumpet, then this model will learn to reproduce the clarinet sound, but as a trumpet. So
まず、クラリネットの音から、トランペットの、モデルを学習して、でそれから、それが、クラリネットの、モデルを学習して、音を再生するそうです。So maybe you can play once more because
so for example,
I talk during you play.
Okay, but so for example, we can also do singing to violin. So I train a model on
歌
violin.
から、バイオリンです。
So input. And I will make it produce it as a violin. And the idea that I have this interaction would be to use our voice to control sound synthesis, so that I call voice-driven sound synthesis. So if we have some vocal imitations, so for example, someone doing a banjo, and I train a model on cello, maybe I can create cello sound with doing my voice imitation, and I get something like this.
歌から、そのチェロの音を学習させてやった結果ですね。
Or for example, someone imitating a crow.
人間が、カラスの鳴きを真似しているものです。
And the model trained on viola will give
それがビオラのモデルトレイン学習させてた。
So that is an intuitive way to generate instrument sound if we can use our voice to imitate an idea that we have and that get the model to play the instrument according to our idea.
Okay.
The second application with this representation is because it is a discrete representation, I can take every feature of the representation and compute audio descriptor corresponding to this feature. And I have a mapping between an audio descriptor. So for example, it could be fundamental frequency or spectrocentroid or bandwidth and other representation. So then I can control, I can give target and find the features of the models that are closest to match to the target and generate audio from the acoustic target.
要約すると、ある、特徴から特徴へと、その、を目指して、合成する方法だそうです。
Okay. So, for example, controlling a violin with a centroid. So this is the figure I show on the right. So it sounds like this, basically. So we see increasing centroid, and then it will decrease. Or, for example, I can take a model on syncing and ask to have a pitch that follows a sinusoid shape. And decrease again. Yeah, so that's another way to interact with the model.
最初は
And you can, for example,
okay, go ahead.
And for example, the user can choose the own curve, the own audio descriptor he wants to control.
その前に、セントロでよってコントロールされたのが、バイオリンで、その後が、その、サイン波の、波形で、その歌という部分が、コントロールされたというのが2番目の、例でした。Okay.
And so to finish, so current experiment that I have in mind, so would be to have more advanced descriptor-based synthesis using something like a Melgan vocoder, but that is trained at generating audio from acoustic descriptors and not from MERV spectrogram. So on the right, it is a MERV spectrogram, and there is only the phase information that is lost. And on the left, there is the corresponding loudness, pitch, centroid, bandwidth, and flatness. So it is a very more reduced information representation. So it is more expressive, but it is also more equivocal.
これは、最後に、これは最後、現在の、研究で、右側の例が、位相だけに、基づいたものと。で、左側っていうのが、このように、上から、音量、音の高さ、セントロイとか、バンドワイズ、というような、ものに基づいて、表しているものです。
And another idea that I'm working on is to use a two-stage model, but this time have a lower level model that is just doing the synthesis and that is pre-trained and freeze. And on top of this model, to learn different other models for specific controls. So for example, using a model that will, for example, learn a 2D representation with one axis that is pitch and one axis that is instrument, for example.
これもう一つの、今現在行っている研究としては、この、例えば、右側の上の部分にあるように、ピッチと、その、楽器のような、二次元の、空間で、再現するものです。
Yes. So to conclude, so about neural sound synthesis, so the synthesis quality has greatly improved and is getting like comparable to classical techniques or to recorded audio. But the efficiency is still very limiting. So, for example, it requires a lot of computation power. It's maybe not real-time capable or not real-time capable on laptop for users.
これまとめなんですけど、そのニューラルサウンドシンセシスは、これまである、サウンドシンセスの方法の音には、近づいてきたものの、実際には、その、効率は、良くないと。で、例えば、ラップトップのようなもので、やろうとするには、非常に困難だろうということです。
And for sound synthesis for music, so there are very little research on the interaction and the implementation of the model for music composition, for musical creativity. And I just put a GitHub link to an ongoing team project with developing interfaces for neural sound synthesis with MaxMSP.
実際には、作曲に、使う、モデルとしては、まだ程遠いわけですが、真ん中の、リンクっていうのは、その、この、ニューラルサウンドシンセシスを、インターフェースを、用いて、実用化するっていう、プロジェクトを今これから行います。
And so for musical sound synthesis techniques with neural networks, I think that we need to have more research into interfaces. So, for example, more research with MaxMSP or Max4Live to apply neural network models. And also, we need to develop models that are efficient enough for being used with normal hardware like MacBook CPU.
この MAX のように、さらにこのインターフェースを備えて、実用化したものっていうのが、重要になってくることと、この例えば、MacBook Pro のような、ものでも、十分に動くように、効率を良くしなければならないだろうと、今後の、課題です。
Thank you very much.
はい、
ありがとうございました。I look forward to your questions or to your emails.
最後、ちょっと時間が過ぎてしまったので、1個だけじゃあ質問、もしありましたら受けますが、何かありますか？または、この、メールアドレスに、質問していただいても結構です。Do you take question now, or you prefer that the
Yes, of course.
Someone write email?
Please. No, I am happy for questions as well.
So far there is no question in the chat. So the
Okay.
someone can write the email to you directly, maybe. 大丈夫ですか？
And I can also send you PDF for the presentation. So there is all the links for GitHub.
You mean you can leave this presentation to the on our
I can give it as a PDF.
この、今の、プレゼンテーションの、ファイルを、PDF にして、サーバーで、OK, so you can send us the email.
Okay. Thank you.
この論文っていうのは There's one question.
Okay.
彼の書いた論文ってことかな。Is everyone can access the thesis that you wrote? Is there any way to access your what you wrote?
Like the code?
No, the article or your thesis.
My thesis,
Yeah.
PhD thesis.
Or anything that
it is
you
not
wrote.
written yet.
That it's not
At the end of the year.
It's not open for the public yet.
I will defend my thesis at the end of the year in December.
もうすでに博士号を取ったと私は思ってたんですけど、まだ、論文は、論文はもう書き終わったんですけど、最終的に、提出するのは、今年最後だそうです。ですので、論文は、まだ、一般の人は、手に入れることはできないそうです。Even you wrote a short one, like you gave some conference, or you don't, it's not opened for the public yet. Any kind of short one. It doesn't have to be your PhD thesis, but like for example, ICMC or anything.
Papers, conference papers.
Paper, yeah, exactly. So paper, I mean.
Yes, of course.
Where that people can access.
I can.
Maybe he can email you.
They can email me, and ICMC is not published yet. But I put the papers on archive. I put the papers on archive as well.
Okay, I will translate.
So I can.
So they can ask by email.
Yes. For the papers, yes.
メールを、してくれれば、ペーパーですね、論文じゃなくて、短い、論文は、すでに学会とかで発表したものは、上げることができるそうです。There's another question. There's two more questions.
ニューラルグラニュラサウンドシンセシスは、フレームをオーバーラップアウトするときにミュージカルノイズは出ないんですか？
When you overlap neural granular sound synthesis, it doesn't cause any noise. When you do a granular synthesis, it's overlapped, so it doesn't cause any noise.
Yes, it's so the waveform windows is not concatenate; it is overlap. So, like this overlap is not making noise because the audio is smooth. Like in the space, the structure of the granular space makes that the neighboring points, the points in the neighborhood, they are matching each other and they can be overlapped. If I take two windows that are not related acoustically, even if I overlap, it will make clicks or it will make noise, but the representation is smooth acoustically, so that's why when we overlap neighboring windows, they are smooth in the audio waveform.
それぞれの、窓っていうのは重なり合ったわけですけど、この、ニューラルサウンド、グラニュラルサウンドシンセスの方法は、 非常に近い、サンプルを、重ね合わせるという方法と考えに基づいているので、その、重ね合わせても、ノイズが起こらないと。ただもしその近い、サンプルじゃなくて遠いものとか、随分音色が、違うものを、そのたとえ重ね合わせたとしてもその場合は、クリックが出るという、ことだそうです。Another question.
And I have a last comment about
Yeah.
this, because classical granular sound synthesis is based on a library of grains. Like the library is cut, and you have a certain number of points, a cloud of points, and then you can take different points in the cloud. But let's say if 2 points are very spaced in the cloud of granular sound synthesis, you cannot generate in the middle. You have to take the 2 points even if they are spaced. And the model that I train, it is learning a continuous representation. So basically everywhere, that's why I can do smooth interpolation, because everywhere is invertible. We can generate audio everywhere in the space, not only on the points of the database.
通常のこれまでにある、グラニュラルシンセスは、例えばサンプルが、どのような音であってもとにかく、雲のように混ぜると。っていうので、そのあるサンプルとあるサンプルの中間の音色とかっていうのは、あまりその全く、考えというかアイデアにないわけですが、先ほど私があまりうまく訳さなかったんだけど、この、ニューラルサウングラニュラルサウンドシンセス考え方はあるサンプルとあるサンプルがあって、その、音の中間を、滑らかに、つなぐことができるっていう考え方なので、その、例えばある、両極端の、音色もこの、自分の意思次第、または、自由に、その、行き来するっていう、要するに、インターポレーションですね、することができるっていう、考えに、基づいているので、従来の、グラニュラルシンセス名前は、一緒だっても、随分根本的な発想が違うということですね。Another question.
あと F0 推定を伴う方式の場合は
何
F0 推定、ピッチ推定、ピッチの推定を伴う方式の場合は、その推定の精度で品質に影響が出ると思うんですけれども、それはどうですかっていう質問。
ピッチの推定がごめんなさいよく。
ピッチの推定をするような方式の場合は、その推定の精度によって品質にその合成された音のクオリティに影響が出ると思うんです。
When you based on the estimation of the pitch, the quality of sound is really depend on that ということかな。Do you see that problem at that point when you estimate the sound with the pitch?
Yes, like for the control with audio descriptor, and the fundamental frequency. Yes. So the model is not trained with knowledge of pitch. Basically, it is when the model is trained, then I take every element of the representation of the model, and then afterwards I estimate the pitch of each of the features that the model has learned. So the pitch estimation is not part of training the model, it is part of controlling the model after it is trained. And for that, there are two issues. The first issue is that because the model that is discrete, it is like quantized, it cannot do like a perfectly smooth pitch. It's sometimes like jumping stairs a bit of pitch, even though I want to have like a continuous envelope. And also because each feature is very short term.
I cannot remember whole things, so I have to translate. But
sorry.
I think the person who asked this question, specific question, he must be specialist. So he understands what you're saying, but I briefly I summarize what you're saying. そのピッチの部分っていうのをその学習の結果じゃなくて、それはすでにまずその教えると。でその結果を学習させるっていうのを今まあすごくかいつまんで言うとそのようなことを言ってます。OK, you can continue. You can continue.
And the second limitation is because the model is learning very short-term features. So, for example, each feature is corresponding to a windows of 100 milliseconds. So because of that, the pitch is not well defined. So also the pitch estimation for controlling is approximate. So that's why when I show the curves, it's noisy. It's following the curve, but with some noise, because features are very short term. So the acoustic quality is not very precisely evaluated.
音の質はそんなに正しく計算されてなくて、でその時間軸っていうのは非常になんだっけ短いって言ったらいいのかな。でだからそのこのカーブもこうやって実際にはだんだんになってノイズが聞こえるということです。まず質問あります。OK, I think.
And for pitch estimation, I'm just using the PyWorld vocoder, like World vocoder. It's a very lightweight CPU, open source.
PyWorld vocoder, you said?
World vocoder.
World vocoder っていうのね、ピッチのエスティメーションに使っているそうです。それはそんなにCPU 使わないっていう。これ最後ですか。最後です。Okay, that's all about the question. Okay, so thank you very much. I mean, some of the things. I mean, I'm not specialist in this field, so I cannot. Some of the things it's over my head, but I think without my translation, these kind of people understand directly what you said, so you don't have to worry about my translation. It's only the max user can.
Thank you very much. Thank you very much.
Maybe some of things too difficult, but even for me, it's a little bit specific subject, so I couldn't completely translate well. But apologize at this point.
No, thank you very much. Thank you very much.
私もこの分野は専門ではないので、随分あまりというかもう全然ですね、通訳になってなかったので本当に申し訳ないと思いますが、多分専門の方は私の通訳っていうのは全然関係なく直接話したことを理解してもらったと思います。むしろもし具体的何か質問とかあれば直接メールしていただいた方がいいと思います。Okay, so thank you very much, and
thank you, Steve.
I hope you coming together again one day.
Yes.
Due to this circumstance of coronavirus, COVID, it's hard to travel, but one day we'll. Okay. Hi.
Yes.
Okay, then. Thank you very much.
I hope I come back to Tokyo as well.
はい、また東京に
Have a good summer school.
戻ってきたそうです。はい、OK。じゃあどうもありがとうございました。OK, thank you very much. じゃあこれで終えたいと思います。はい、じゃあどうもありがとうございました。はい。